Thank you so much. Thank you to the organizers. It's wonderful to be here with such energy. I think we're all here because we live on a marvelous blue planet that is special because it's full of life. It's full of chemistry. It's full of amazing organisms that can pull resources out of the environment, carbon dioxide from the air, and turn them into marvelous, functioning, self-repairing, adapting, moving, sometimes even thinking machines. I'm an engineer who has always been inspired by this incredible diversity of the biological world, and particularly by this chemistry. Because, I mean, face it, we need chemistry in our daily lives in order to make the food that we eat, the fuels that we use, the textiles. And if we are going to stop pulling that chemistry by pumping oil out of the ground, we have to be a little bit smarter about how we do that. And I'll tell you that the best engineer on the planet and the best chemist is this biological world. And the major players in this are these remarkable machines called enzymes that catalyze all the reactions of life. Incredible diversity of chemistry that no human being can master. And when I was a young person, at the beginning of my career, I decided that I wanted to engineer enzymes. I wanted to build new enzymes that would serve human purposes, that would allow us to live and do chemistry in a way at least partially comparable to nature, that can use abundant renewable resources and do it in a way that's cyclable and sustainable. Now, this was a hard problem because back when I was doing that, everything was difficult in engineering a protein. It's still difficult today because what are we trying to do? We're trying to take the code of life, the DNA that encodes one of these complex molecules, and rewrite it to do better than nature, to do something that nature perhaps didn't care about doing. Back then it was hard. Today it's a little bit easier because we have these incredible tools of molecular biology, this is 30 years later, that have come about that allow us to read DNA. You can sequence any DNA you want now. And from that, we're learning so much about the code of life. You can write DNA. You can email your favorite sequence off to a supplier, and you'll actually get the physical DNA in the mail. We didn't have that 30 years ago, but now we do. You can edit DNA. We all hear about the CRISPR revolution. You can go in and modify DNA at will. It's easy to do. But what we don't know how to do is compose it. To me, the code of life is like a Beethoven symphony. It is so intricate and beautiful. And no human being, we can read, write, edit, but no human being knows how to compose this, even for a single enzyme that can match the power of natural systems. As an engineer, I sat down and said, well, gosh, if we don't know how to do this, what can we do? And it turns out there's a marvelous design process that nature came up with that gave rise to all this remarkable diversity of life, right? It's called evolution. One recipe for adaptation, optimization, and innovation in the biological world that's simply mutation and natural selection. It's like turning the crank, and out comes all these marvelous solutions to the problem of being alive. So why not use that process to build something new, to go into the future and dream about how biology could solve the problem of sustainable living on this planet? So I love to antagonize biologists by relegating them to that tiny little green space in the universe of possible life. So you think about what are the proteins that would be possible, or even the life forms that could be possible if you now took control of evolution at the molecular level. And it really is a universe. The space is impossibly large. It's got the solution, the cure to cancer lies out there. The solution to living a long life. Maybe even the cure for taxes might be there. But you've got to find it. It's a wonderful space to explore. So everything that biology has explored all the way back to our last universal common ancestor that you heard about yesterday, that fits in a tiny fraction of those possibilities. Now you're free to go out and try to find all these interesting things in this space of possibilities. And so I might ask you to think about how far could we go, with one problem, chemistry. If you now could use evolution to do chemistry, where could you go? Could you create new forms of life? We talked a little bit about silicon life forms. Well, could you make and evolve something that uses bonds never even found in nature? What would that life form look like? What would it do? Practically, could you create organisms or even just catalysts that could make the products that we need in our daily lives with a programmable microbial factory, all churning out, instead of more microbes, churning out our materials that we need or our fuels. Now, this is not a new idea, right? We've been doing this for a long time. Human beings have been modifying the biological world at the level of DNA, using evolution by artificial selection for thousands of years to make things that serve us, everything from corn to carrier pigeons, lab rats, racehorses. We make things that help feed us, that comfort us. This right here is not remotely natural. It would not exist were it not for the impetus of human beings, the control on evolution. In fact, it's not even fit. If that got out in my neighborhood in Los Angeles, it would be eaten. We have a lot of coyotes and mountain lions. But it serves our purposes. And of course, in the past, and in the farmer's barnyard and in the laboratory, well, not so much in the laboratory, but in the farmer's barnyard, and if you're breeding cats and dogs, you've got a very limited control over the underlying genetic diversity for evolution, right? So in nature, monkeys go with monkeys and worms go with worms, but probably not going to get much of interest or beauty if you cross those. You can control your rate of mutations by smoking a few more cigarettes, but you really don't have a lot of control over making new molecular diversity at the level of DNA. But remember, that's changed, right? Now, in the test tube, you can make any DNA you want, so you can have 3 parents, you can have 33 parents, you can breed monkeys and worms if you like that. Just to remind you, we do not make Wolford. Wolford is my lab mascot. That's just for your enjoyment. That's not what we're trying to do here. We're trying to make enzymes, so I'll bring you back to that. So we recombine DNA and mutate DNA in the test tube in order to do this new chemistry. And we have this power now. Think about it. You have the power to control the underlying diversity for evolution in a way we never had before. And that power is nice, but you have to know what to do with it and how to control that in a way that you get something useful in a short period of time. And so think about some of the numbers here. A typical protein, 300 units long. There's 20 letters in the possible alphabet. So you've got, for a single enzyme, 20 to the 300th power of possible sequences. It really is a universe beyond a universe of possibilities just for a single protein. And there's a marvelous short story written by Jorge Luis Borges, The Library of Babel, that describes the library of all possible books. And those librarians threw themselves off the balconies in despair because all they found was gibberish. All the books were random letters, never had a meaningful sentence, much less Moby Dick. And so, or the true story of your life. It was filled with all sorts of false stories of your life. But nobody could find anything. And so here we are wanting to explore this library of proteins, and we have the control to make the DNA, but we don't really know what are the processes for exploration. Because even if you make 3 mutations, you have billions of possibilities. And as you make more mutations, it just grows exponentially. So we had to figure out what are the ways to do that. You were briefly introduced to this gentleman, John Maynard Smith, yesterday. And I'll bring him back because he gave me comfort in my early days of this exploration by explaining that if you consider all possible proteins ordered in such a way that an existing protein is surrounded by its single mutant neighbors, and on and on. So many thousands of dimensions, but just think of your library being ordered that way. In order for evolution to work, Maynard Smith said, and he believed it did, then functional proteins must lie next to one another. Because the probability of making multiple mutations simultaneously and finding anything beneficial is very small if you can make single mutations and walk through this space, essentially all the way back to the origin of proteins, then evolution can happen. And this was an important and useful idea for me because I wanted to make better proteins. And if you have a fitness landscape, so think of your desire for something better as being the new definition of fitness. I decide who lives and who dies and who goes on to the next generation. Remember, it's just microbes. But I decide what fit means, and if this landscape of how fitness maps to sequence is very rugged, then all mutations send you to crevasses of non-function, and it's not a very fun experiment. But if the landscape is smooth, anyone can optimize a protein by a random uphill walk. You just blindly walk around, find the uphill step, and keep going. And this, then, evolution can happen. And based on Maynard Smith's arguments, we felt that the landscape had to be smooth in some of its dimensions, and therefore we would be able to apply very simple process, something you can do in a high school laboratory, to evolve new enzymes. So basically, you take a protein from nature, a gift of 4 billion years of evolution, right? Or whenever proteins came about, pretty close to 4 billion years ago. And that gift, a rare functional molecule, can be optimized by making mutations. That's easy to do. Polymerase chain reaction, for example, will make lots of mutant DNAs. Cells do the hard part. They translate that into proteins. The hard part for the human being is to decide who is performing better, let's say an enzyme that catalyzes its reaction faster. Most mutations are deleterious, and in the old days went to the trash can. In the new days, they go into machine learning algorithms. And then if you've asked the right kind of question, you can iterate on this and improve the performance of an enzyme. So it looks like this, where you take something from nature that has been optimized for its natural job. When you ask it to do something new, it's generally a little less enthusiastic about that. So you start from here, but you can optimize it through this turn the crank iteration of mutation and artificial selection to re-optimize it for a new function. And that's what people have done. They've used this process because it's so simple. Nature invented it. Human beings invented it, and it's been improved over the years to make everything from the laundry detergent enzymes that you use. This has reduced energy use in laundry because you can now wash in cold water, and that's a real benefit. Merck makes its blockbuster drug Januvia using enzymes made by directed evolution. Why is that important? It completely reduced the organic solvent waste that's used in the manufacturing these drugs, and now we don't have to use precious metals as catalysts. You can just have bacteria that make your catalyst for the price of sugar. Many other industries. And I put this in here because there was a little discussion yesterday about how could we have renewable fuels. Back in the 2000s when oil hit a really high price, it was over $100 a barrel in the United States. we found, two of my former students founded a little company in Colorado that took over an ethanol plant and turned it into a plant that makes jet fuel. Microbes can be trained to make jet fuel. And so now this company, it's still in business, and they will supply as much jet fuel as anybody's willing to pay for. And the problem is that we're not willing to pay for the real cost of making these things from renewable biomass, because biomass is expensive compared to oil as we continue to pump it out of the ground. But biology can do this. We have the technology to do these sorts of things. I became very interested in how evolution not only optimizes an activity that exists in nature, but how it can actually innovate and create something that you can't go to a database and find a starting point for. And I just described a very conservative process of accumulating single mutations. And you might ask, well, gosh, how do you create a new species of enzyme? A new species of enzyme would be something that catalyzes a whole new reaction, maybe even a reaction invented by human beings. You know, God forbid, those human beings have been pretty clever about chemistry. My colleagues, will pat me on the head and say, oh, biology is really cute, that's really nice, but biology can't do what I can do. And in fact, the chemicals industry is not run by biology, it's run by chemistry. So why not get biology to do what humans have been able to do? And that can be done because if you think about it, biology innovates all the time. Biology innovates enzymes, creating new enzymes to break down man-made materials that have been on this planet for only 50 years. Biology is learning how to eat plastic bags slowly. Biology is learning how to counteract pesticides that we put out, antibiotic resistance. Biology responds very quickly. And the way that she knows how to do this is that even though an enzyme might be selected today for the chemistry it does, it has many other capabilities, kind of like you students, right? You might be selected for your ability to study really hard and do well on tests, but maybe you play the piano. Maybe you can do dishes if you have to. You have many capabilities that might be drawn out at any one time. You're good at sports. So are enzymes. And if I'm the breeder of enzymes, I have to recognize those capabilities and train or breed the enzyme to exhibit those new capabilities. So once I find, we call these promiscuous activities of existing proteins, to do new chemistry that has never been important to nature, I can draw this out through this optimization process of evolution. All right, no, bar the doors. I'm going to hit you with a little bit of chemistry here because I want to give you an idea for how you do this. We look at the chemistry of the natural world and a family of enzymes that I've had a long history with because it's so diverse. So much powerful chemistry. It can take an oxygen from air and activate it in an intermediate that then allows it to transfer oxygen into things like oil. You can make very powerful chemical transformations with this enzyme. And nature diversified it, presumably through a process of discovering these promiscuous activities millions of years ago, into a family that catalyzes all these chemical reactions. And we argued that we could do the same thing in the laboratory if we could convince the enzyme, instead of making a reactive oxygen, for example, to make a reactive carbene. And then it would transfer that carbene into other substrates and do chemical reactions invented by human beings, never known in the natural world. And that would be enabled, just like we do with antibiotic resistance. If you put man-made substances into these enzymes, they learn how to use those, and then you can use directed evolution to create a whole new catalyst. So we made crazy things like highly strained rings, bicyclobutanes. Here's a molecule that you never find or almost never find in biology. And when biology makes it, it's not through a process similar to what I'm describing here. And I'll show you this carbene transformation was never known to be catalyzed by earth-abundant iron. In chemistry, we want to replace precious metals with earth-abundant metals. And we would love to be able to use iron because that's dirt cheap. So you can train an enzyme to make crazy strain rings like these cyclopropenes. 56 kilocalories a mole of strain energy. Humans have a hard time making these things because they fall apart really readily. But an enzyme can be trained to take a triple bond, add a carbene across that, so we drive the formation with this man-made compound. You add a carbene across that, you can make these cyclopropenes. And the idea is that if you can find somebody who has a little bit of activity, and I have a lot of these in my refrigerator, then you can evolve it or breed it over a few generations to make something that's useful. But even more cool, you can convince the enzyme to hang on to this cyclopropene and add another carbene across it and make a bicyclobutane. That's like rocket fuel. These things can be put into binders for rocket fuel, and they're all made by bacteria. Nobody ever thought that this was possible, but Kai Chen trained the enzyme to make single diastereomers of bicyclobutanes. Now, nobody's been beating down my door for bacteria that make bicyclobutanes, but that's because they never had these before. And it was a fun example. We talked a little bit about silicon-based life yesterday. Lots of people have asked that question for a long time. You know, we've got all this silicon on the crust of the planet. Why does life not put silicon in place of carbon? There's no examples known. You can go through all the literature you want. There's no examples known. That doesn't mean it's not out there. But no chemist has found carbon-silicon bonds in the biological world. But by golly, if you go ask nature if she can do it, you will find, for example, in this hot, salty pool in Iceland, there's a cytochrome C that when you give it a dimethylphenolsilane, so a silicon H bond, and this carbene precursor, it will make a carbon-silicon bond. All you have to do is ask. And it does it as well as any human has ever done. And it makes just one of the stereoisomers. It's one of the enantiomers of this. And this is crazy. This protein is super stable. You can boil it. You can even give it to a chemist. They can't even ruin it. And it will catalyze that reaction just as well. But even more interesting, it will evolve. So you can play the same games. You can take this protein from nature, whose native function has nothing to do with catalysis, but it has a nice hot iron atom there. And you can mutate it and select it over a few generations and make something that's 100 times better than anything that a human has ever done for this chemistry. When we published this, we got a lot of press because it is a story that captured people's imagination. Here's a whole bond that was never found in nature, but nature can do it. Nature's already there, poised to do this chemistry if it ever becomes beneficial. And in my hands, it became beneficial because I said, you die if you don't do this. So it learned really, really fast how to do it. And the reporter didn't want to have anything to do with the chemistry. It's really hard to report on chemistry. So he had Spock and Captain Kirk from Star Trek with the silicon-based life form. I know you probably don't watch this episode, but it's a cool episode. They're talking about, the Horta, the silicon-based life. And nobody read the paper, but when the paper came out, they all read this article. And so I said nothing about silicon-based life in the paper. The paper has nothing to do with silicon-based life. But they read the journalist report, and so Popular Science says, I don't think so. If you really want to know why there are problems with silicon-based life, this is actually a very good article. Popular Science does a good job. Astrobiology didn't do such a good job. They said, oh yeah, because they want this thought that you could have it grow. Once again, nobody read the paper because it's 130 pages of supplementary information and NMR sequences, spectra and things like that. But they said, oh, silicon-based life is going to grow. The intelligent design community. Oh my goodness, these are the anti-evolution folks. So they read the paper and they said, what kind of spin are we going to do on this? Well, they said, that's intelligent design. And I said, oh yeah, that gives me credit for intelligent design because evolution is intelligent design. It really is. It is the most intelligent way to design. So I can't argue with that. And by the time it got to the Twitterverse, we were rolling on the floor laughing. So if you ever, I now put all my papers on Twitter because I want to get the comments back that give us some entertainment there. But why is this interesting? I mean, it's fun. It's a lot of fun. But it's interesting because my colleagues who criticize the chemistry of the biological world are right in some sense, right? Because if you look at the carbon X bonds known in biology, carbon goes with nitrogen, oxygen, sulfur, some halogens, a few other things, but there's vast swaths of the periodic chart where it doesn't go, where humans have gone, where it's useful to go. I mean, think carbon-silicon bonds. There's 50 products in this room made by human beings in your hair, lotions, caulks, sealants, paints. It's a huge industry, all made by human beings, and there's no biological system that can do it until now. In just 2 years, we added not just silicon to this periodic chart, but also boron, another extremely useful element that nature does not utilize, but was very easy to convince bacteria to incorporate boron into organoboron compounds. So nature can do it if you know how to ask her appropriately. Just recently, we also had added a whole new way to make carbon-carbon bonds. Nature knows how to do this, but there aren't that many ways, like methyl transferase enzymes. Very powerful, but not easily modifiable. But if you take a reactive carbene, you can now add the carbene to a carbon H bond and form new carbon-carbon bonds, which is a very hot area of chemistry because you can modify drug compounds, for example, very readily with that. And so we've just been able to go through a whole litany of chemical reactions that human beings thought that they invented. And it turns out that some of them not only didn't invent it, that they were already found in nature, but many of these systems are so much better. The carbon-boron bond system, we were able to do 400 times better than the best human catalyst ever made. So this is the power of biology. And I'll just end with one thing. Oh, this is the carbon-carbon bond. Why do you want to do this? If you can convince an enzyme, instead of to make these reactive oxygens, to make reactive carbenes and transfer that to a carbon-hydrogen bond, you can do things like late-stage alkylation of drugs. And maybe you don't care about that, but nature's already made hundreds of thousands of catalysts that are in our databases that you could modify, that could take almost any substrate. These P450s, you have 50 of them in your liver that detoxify all sorts of compounds that you might be eating or ingesting. And there's so much diversity in their capabilities, now you can evolve them into making new carbon-carbon bonds. And I'll end with just one last story, because what this is, what I want to do is open a door of where we can go in the future to live sustainably. What I told you about reactive carbenes, you can do exactly the same thing, or not exactly, but pretty much the same idea with reactive nitrines. And this is a wonderful story because when we first showed that you could transfer nitrines, after that, people started looking in nature to see if she actually did this. We were the first to publish it, man-made enzymes, but then people discovered natural enzymes that already do this chemistry. And just today, a paper was published in which we were able to take a simple hydroxamate precursor, so these are really cheap molecules, make reactive carbenes, nitrines here. And once you have a nitrine, that nitrogen can come and attack this CH bond and amidate it and make things like beta-lactams. Beta-lactams are powerful antibiotics. And here's an enzyme that can make this strained 4-member ring in one step from a simple precursor with 1 million turnovers. What does that mean? It means it does it 1 million times. No chemist can do this. Only the chemistry of biology can do this, and do it with perfect selectivity. And no chemist can do it because in chemistry, you often have trouble with side reactions. This is where biology is powerful. Biology is selective. That's why she's so clean, because she can take a desired product and suppress side products that are like eating money. You know, you're chewing up money when you're making these side products. The humans don't know how to stop this, but the active side of an enzyme can catalyze this reaction, making only this product and stop the side products. And if you're not impressed by that, you can tune it with evolution and do chemistry that's even more amazing, because you can take a molecule like this one, where you could come back and form a ring here, and you can tune the enzyme so that it makes one beta-lactam, a gamma-lactam, a delta-lactam, whatever you want, completely overriding the inherent reactivity of these bonds. So what am I trying to share with you? I'm trying to share that nature has the most powerful evolution algorithm, the most powerful design process. There's nothing like it in the engineering world. It works all the way from molecules to ecosystems. So we can use that. Nature has the most powerful chemistry. We can use that, and we can put them together in ways that we couldn't in the past. And this is such an exciting area of research, because now you can take 100 years of chemical knowledge and creativity of human beings and marry it with the powerful world of biology, so that someday we actually might be able to have biological factories that use abundant renewable resources to make what we want. So I want to leave you with this idea that who cares about the Internet of Things? I know we all like the Internet of Things, but it's the Internet of living things. This is very much what Sandra was talking about. The warp and weft of the biological world. Well, that's a very innovative world. I mean, life will survive. It will be different, probably, from what we're used to. Life will survive, and it's doing problem solving all the time, 24/7, for some billions of years. I think it's fun to discover where life can solve human problems. And with that, I'll thank the people who actually do this work, who are young people interested in creating a sustainable future for us, and at the forefront of engineering, computer science, and science. Thank you.